All right, in this video, you're going to have to forgive my hoarse voice. We're going to do Chapter 11, Neural Nets, or otherwise called Neural Networks. Maybe you've heard of these things. They're kind of popular right now. They're very powerful and are used for prediction and classification. And the basic idea behind neural nets is to mimic the model of the brain. And in other words, you have nodes and you've got synapses, and between these nodes and synapses, the information is sent back and forth, and that information can be used to then change the structure of the network. So in this network, we have multiple layers. The input layer is the raw data that we have, and then there are hidden layers, and the hidden layers we don't ever see except for when we look at the output. And then we have the output layer, which gives us the results of the prediction or classification. So these layers are made up of nodes, and the nodes are all connected to each other in the different layers. We'll look at an example of that in just a minute. And we have weights that are basically coefficients that tell us how much each of the nodes contribute to the next layer, or the nodes in the next layer. And then finally, we have what are called biases, and you can think of those like constants in a regression model. And here we have a schematic diagram of a neural network. Now, here we have the input layer. So in this example, we would have 1, 2, 3, 4 different input variables, and we have 2 hidden layers. The first one has 3 different nodes. Here they are, 1, 2, and 3. And the second one also has 3 different nodes. And then finally, we have a single output layer and 1 node in the output layer. It is possible to have more than 1 node in the output layer. But the idea here is we're going to come up with some sort of weights that connect each of the nodes. So here we've got weight 1 for the first input, weight 2, and weight 3, each going to each of the nodes in the next level. And then we're going to have theta, we'll call it theta 1 just for fun right now. And that is going to be the values that are multiplied by each of the components in the previous layer, each of the nodes in the previous layer, and then those can get added up. So what's going into this node is actually from down here, there's 4 inputs to each of the nodes in the second layer, the first hidden layer, and then there's 3 nodes in that layer, so there's 3 inputs to each of the nodes in the third layer, and then those are combined into 3 inputs into the final layer. So the idea here is to come up with the weights at each of these stages that give us the best fit to the training data, but then also give us the best fit to the validation data. Now, the size of the neural network can be quite large, quite extensive. Typically, you're going to have just 1 hidden layer, but there's nothing to stop you from having multiple hidden layers. And the only problem that you run into by making the model more complex is that you tend to start fitting the data too well on the training set. And that causes problems because then you start fitting noise, and when you go to the validation set, you find out that your model is maybe not as good as you thought it was. So let's look at an example. This is a small example where we're measuring the acceptance of cheese by consumers. And by acceptance, we mean people sample the cheese and say, yes, I like that, or no, I don't like that. And the 2 input variables we have are fat and salt. And these are scores, so I don't know what the measures are on those. But you see we have 6 observations, so this is a very small data set. And we're going to follow this first observation through to see what's going on with the neural network. So we have 1 node for fat, 1 node for salt, and we're going to do one hidden layer with 3 nodes. So we have these weights, W13 and W23, that go to node number 3. So they go from number 1 and number 2 up to number 3. And then we have theta 3, which goes along with node number 3. The weights for node number 4, the contribution for node number 4 would be W14 and W24. And the idea here is you take the value of fat, whatever that number is, multiply it by W1, add to that the value of salt, multiply by W24, and then add theta 4 to that, and then operate that input through a function. So let's look at that in a little bit more detail. For the record number 1, we have fat input of 0.2, salt input of 0.9, and we are going to propagate these values through the network, and finally we're going to end up with output J, and this is what's going to be the value that goes with node J. And that's just going to be some function of the bias plus this linear function of the weights times the values coming from the previous layer. So where do these weights come from, and where does the theta come from? Well, they're going to be randomly assigned at the first iteration, and typically use a value between negative 0.05 and 0.05 for these things. And when you do this, you really have no predictive power whatsoever in the model in the first iteration. Now these are just used initially, and the idea here is that we're going to update the weights repetitively as we add more data and run through the data set over and over and over again. So if we want to look at node number 3, and if we're using the logistic function for our nonlinear transformation of the data, we would see that our output at node number 3 is equal to 1 divided by 1 plus e to the negative, and this is just like we talked about with logistic regression. We have this linear function up here, and so we put all these numbers in and we get out a 0.43, which then is pushed forward to the next layer. So here's how it works, and you can see here we have a negative 0.3, that's this negative 0.3 right here, plus 0.05 times 0.2. This 0.05 again is random, plus 0.01 times 0.9. So here's the 0.9, that's the salt value, and then the 0.01 is the random starting weight. And so we take those numbers, add them up, raise it to the negative e power, add 1, divide that into 1, and that gives us back essentially a probability. And so the value at the third node is 0.43, and we do the same thing at the fourth node and the fifth node. And of course we get different values because we have different weights and different biases. So for node number 4, we would have 0.02 minus 0.01 times 0.2 plus 0.03 times 0.9. Run that through the logistic function, and we get back 0.51. And we're going to do that again until we finally get to our output layer, which says node number 6 has a value of 0.481, and node number 7 has a value of 0.506. Now you could think of these as probabilities if you like, because they are between 0 and 1, but you will notice there's a problem with doing that, and the problem is that these things do not add to 1. So we have all possible outcomes represented. Either you dislike the cheese or you like the cheese, but the probability doesn't sum to 1, so that is not a proper probability distribution. So at this point, we couldn't really say that there's a 48% chance that someone will dislike cheese where the fat content is 0.2, and the salt is 0.9, because, again, those things don't add up to 100%. But these are the only outputs that we have, and so we can simply normalize these things so that they do add up to 100%. And the way we do that is we take the total, 0.481 plus 0.506, which is 0.987, and divide each of the respective values into that. So we get 49% for the probability that somebody will dislike the cheese, and 51% for the probability that someone would like the cheese. So at this point, you might be saying, this is a very complicated model, and you're right, it is, although we actually would not call this a model because we're not doing the same sort of thing as we would with regression in terms of trying to understand what the components of the model are. And in fact, it turns out that if we have our function g just be the identity function, then we can see that this is actually the same thing as linear regression, where we would have just a single node and no hidden layers. And we could do the same sort of thing with logistic regression, because you'll remember logistic regression just says take this function and apply the logistic function to it. So obviously we're not done at this point, because we have a random starting value for our weights and our thetas, and they may be good and they probably are not any good. So what we want to do then is use our training data to fit a model and then look at how the model performs on the validation data. And we start with an initial pass where we're going to use the random weights that we described already. And for each record, we're going to compare the predicted value to the actual value, and the difference is the error, and then we're going to use that error in what's called backpropagation in order to change or update all of the weights. So the error is going to be taken from the output node k, so this is the final layer of the model, and we're going to say, what's the prediction? K y hat. And so the error is yk minus yk hat, and then we're going to multiply that by a correction factor. And when we have the error, we can then update the weights or the bias by multiplying the error by what we call a learning rate, or this L right here. And so if our error is big, that means we're going to make a big adjustment to the weight. If the error is small, then we're going to make a small adjustment because we're probably close already. So we have what's called case updating, where the weights are updated after each record is run through the network. So you would run the first record through, find your weights, and then you would update those based on the error for that record, and then run the second record through. And then you would do that for all of the records, and that would make up what we call an epoch or an epoch, depending on how you want to say that. You can also call it a sweep or an iteration. And this process is repeated over and over and over again until some stopping criteria has been met. The other type of updating is what we call batch updating, where all the records in the training set are fed through the network before any updating takes place. And that's, I guess, the scenario that we described before the case updating. And the math here gets a little bit more involved because the error that is used is a combination of all of the errors from all of the records. And this works because big errors lead to big changes, small errors lead to little changes, and eventually, as you do this thousands of times, then the weights are going to stop changing, and when they stop changing very little, that tells you that you're done. That's one way in which to stop. Another way is when you reach a misclassification rate that you're after, and another stopping rule comes when a time limit or computational resource limit has been reached. So the updating, the back propagation can actually be fairly computationally expensive, and a lot of software, including JMP Pro, use an approximation to that by maximizing the likelihood. And the results are very similar to back propagation, but not identical. However, it is generally a lot faster to do the maximum likelihood estimation because you only have to do one calculation, or the computer does one calculation. So one time through the data to get summary statistics, and then the maximum likelihood is estimated. Models can fit with the neural network methodology tend to overfit the data, and that's something that, of course, we don't want to have happen because we know that we cannot explain noise. We can understand the variation in the noise, but when it comes to actually making predictions of noise or randomness, that is not something that's possible. So to avoid that, JMP uses a penalty parameter and then also requires cross-validation. So the neural network process in JMP says set the penalty to 0, use random weights for starting values, vary the penalty parameter, and then for each value of the penalty parameter, search for weights to minimize the error, and then select the model with the lowest cross-validation error. So this sounds like the whole data mining process all wrapped into one fell swoop, and in fact that's what's going on once you specify the composition of the neural network and turn JMP Pro loose on it. It will do exactly this and come back with the best neural network on the validation set. So here's an example of the output for our cheese acceptance data set, and you can see that we have one hidden layer with 3 nodes. We've got a fat score, a salt score, and after the criteria have been met for stopping, we're using the maximum likelihood estimates in this case, we see that the weights are given here. So hidden layer 1, node 1, fat score is multiplied by 15.08, and the salt is multiplied by 4.31, and then we add to that negative 4.42, and whatever the function is that is used for this, the output is negative 1.49, and so that's going to be combined with the value at this node, which again is going to come from putting in a fat score here and a salt score here. So we'll get a unique value here, multiply that by negative 1.49, do the same thing here, multiply by negative 0.94, same thing here, multiply by negative 1.52, add those up, throw in a negative 0.69, and that will tell us whether we accept or do not accept, or like or dislike the cheese. So the output that we get in JMP looks like this, and you can see we've got a training set and a validation set, and there are several different measures that we haven't talked about. Generalized R squared, for example, entropy R squared, and we're not going to get into those, but RMSE, we did talk about that. Mean absolute deviation, we looked at that, and then also the misclassification rate, and this is the big one that we want to look at in when it comes to data mining. We also get the negative log likelihood, again something that we didn't really talk about, but that's what's used to be maximized in order to get the weights that we want. And so we see classification rate on the training data set is 25%, and misclassification on the validation set is 0. We get confusion matrices with the different rates, and we can see that we only have 4 observations in the training set and 2 in the validation set. So in the training set we get all but 1 right, and in the validation set we get everything right. And so we can see the outputs with the most likely acceptance column added on here, and we can compare that with the actual, and this is the only one that is misclassified. So up to this point, things seem pretty straightforward and maybe even easy to understand, but you got to keep in mind here that we're really dealing with a black box, and a black box is something that by definition you don't understand, or you don't try to understand. So we put our inputs in and the results come out, and we don't really question too much what's going on the inside. However, we can't really do that, and so what we have to do is determine what our neural network is going to look like. This is something that you just can't leave up to chance, and there's no real good automated way to do this. So first thing you have to do is determine how many hidden layers you want to have, and usually one is going to be sufficient. In certain cases you might want to add more, but there's no real good consensus on what it means to add more, other than you're making your model more complicated or more complex, which can have problems. The next thing you need to know is the number of nodes that you're going to use, and there are lots of different guidelines for this. One is to use the same number of nodes as you have predictor variables to start with, and then try models with a little more or a little less and see where you end up with your misclassification or error rates in the validation set. Usually the more complex your model, the better the chances are of overfitting, so you don't want to do that. You also have the choice of activation functions, and these include the hyperbolic tangent, the linear and Gaussian, and others. You also have the option of just saying how many TORs you want to have. When we say TORs, that means how many times is JMP going to restart the model fitting algorithm. And every time it restarts, it's going to have a different random set of weights that it starts with. And you'll find that oftentimes just having different weights is going to lead to a different model in the long run with different misclassification rates. So if you do a lot of TORs, then you're going to, in theory, be able to have a better fitting model in the long run. You also have the learning rate that you can specify, and that has a lot of potential for slowing down the updating of the weights, but it also has a chance to cause overfitting. The advantages of neural networks are you get good predictive ability. You can also capture very complex relationships, and there's no need to really specify a model other than what the architecture of the network looks like. In other words, how many nodes and layers you have. Disadvantages are, again, this is a black box prediction machine. There's no real insight as to what variables are driving the outcomes, and there's no variable selection mechanism here. So you really need to go through and do some variable selection, like either principal components or even logistic regression or multiple regression fitting to see which variables you want to put into the model. And this can be very computationally expensive if you have a lot of variables especially, so that's another drawback. The people at SAS, the makers of JMP software, have thought about all this, and there are tools inside of JMP that allow you to deal with all of these disadvantages. So in summary, neural networks can be used for classification and prediction. They are very good at capturing complicated relationships between the predictor variables and the outcomes. The network is going to learn, and models are updated iteratively, especially as more data is fed into it. There's always a danger of overfitting. Typically, you're going to need large amounts of data in order for this to work well, and even if you do, this is still a black box. So it's very hard to intuit what's going on inside of the model. And so that's all I've got for this video. Look for at least one other video in the folder, the weekly folder, where we look at an example from the textbook. Send me email if you have any questions, and we'll see you later.